Welcome to The Explainer, where we break down big ideas. Today, we're diving into a really huge breakthrough in quantum computing, something that tackles one of its oldest, most fundamental problems. And this isn't just some clever riddle, It's literally the core challenge facing the entire field of quantum computing. I mean, if you're going to build a machine to solve the world's hardest problems, you've got to make sure its most basic parts actually, work. Okay, so let's dive right into this core problem. See, the incredible power of a quantum computer comes from its most fundamental piece of information, but that's also where its greatest weakness is hiding.
So think about the bits in your phone or your laptop for a second. They're incredibly stable, right? Just a simple 0 or a 1. But qubits, they exist in this super delicate quantum state, this superposition of both at the same time. And the slightest little thing, a tiny vibration, a small change in temperature, can completely corrupt that state. And just like that, you've got errors that can ruin your entire calculation.
So to get around this incredible fragility, scientists came up with a truly ingenious idea called quantum error correction. And the concept behind it is actually pretty straightforward. But man, the execution is, it's incredibly complex. The solution really is teamwork. Instead of putting all your trust in one single fragile physical qubit, you bundle a whole bunch of them together. They all work as a team to represent just one piece of information, and they're constantly checking each other for errors. And this robust error-corrected team, that's what we call a logical qubit. And this just illustrates the concept perfectly. I mean, what you're looking at here are real, individual atoms, and each one is acting as a physical qubit. It's wild. In the experiment we're talking about today, researchers actually arranged up to 85 of these atoms just to form 5 of these powerful logical qubits. But here's the thing. Even with this really powerful error correction, there's another major hurdle to overcome. It turns out that protecting the qubits actually limits what you can do with them. Yeah, it turns out this whole error correction thing is kind of like putting the qubits inside a protective bubble. Sure, it keeps them safe, but it also restricts them to this very limited set of simple, safe operations called Clifford gates. And here's the big catch. A quantum computer that can only do these safe operations, it offers no real advantage. You could just simulate the whole thing on a regular laptop. So the crucial point here is that we need to inject a special ingredient to unlock the computer's full potential. And fittingly enough, these are called magic states. When you combine one of these magic states with those simple Clifford gates, boom, you can suddenly perform any quantum algorithm you want. You get true universal computation. And that brings us right back to our original problem, doesn't it? These absolutely essential magic states, they're just as fragile and noisy as everything else in the quantum world. So when you first create them, they're messy, they're imperfect. So how on earth do you purify them? All right, let's get to the truly elegant solution that was demonstrated in this new research. They literally built a quantum distillery. The idea is brilliant. You take a whole batch of low-quality, noisy magic states, and you distill them down into one state of exceptional purity. So the whole process kicks off with several of these imperfect, noisy magic states. You can kind of visualize the noise as this fuzzy, undefined shape here. I mean, it's close to what you want, but it's just not pure enough to be useful for any kind of complex calculation. So, the researchers implemented this process called magic state distillation, and in this case, they used what they call a 5-to-1 recipe. It goes like this. First, you take 5 of those low-quality logical magic states. Second, you run them all through a special quantum distillation circuit. Then, you measure 4 of the states. These 4 act like checks, basically telling you if the whole thing worked. And if they get the right answer from those checks, they know that the 5th, final state has been successfully purified. And what's really cool about this is how it visualizes the process. You can honestly think of the quantum circuit like a funnel. It takes in these 5 noisy inputs, and then, through a series of very carefully protected quantum operations, it filters out all the errors, concentrating all that magic into a single, refined output. And this is what you get at the end. A single magic state with a much, much higher fidelity. And you can just think of fidelity as its purity or its accuracy. It's way purer than any of the individual states you started with. This distilled state is now a top-quality resource, ready to go and power a universal quantum computation. This theory of magic state distillation has actually been around for a while, since 2005. It's considered a cornerstone for building a fault-tolerant quantum computer. But the big question has always been, okay, That's great on paper, but can you actually build one of these distilleries in a lab and prove that it works? So, did the quantum distillery actually work? Let's take a look at the data. This whole experiment was done on what's called a neutral atom quantum computer, and the results? They're pretty remarkable. The results are just crystal clear. They tested this on two different kinds of logical qubits. So in the first case, you see on the left, they started with an input fidelity of about 95%, and they managed to distill it all the way up to 99.5%. Then, in a second, more complex case, on the right, they took an even lower input fidelity, 92.5%, and boosted it all the way to 99.1%. I mean, this is just unambiguous proof that this distillation process really works. Let me put it another way. The process actually suppressed the error rate, the infidelity, by a factor of up to 12. That is a huge leap in quality. It shows you can take a noisy, almost unusable resource and refine it into something incredibly reliable. And again, this isn't just some simulation. This is the actual machinery at work. In those images up top, you can see the real arrays of individual atoms being physically shuttled around. And those movements, they correspond directly to the circuit diagrams you see below. This is the processor executing all these complex steps for error correction and distillation in real time. So, the big question is, why does proving this in a lab matter so much? What does this actually unlock for the future of computing? Well, as the authors of the study put it, this isn't just some small, incremental improvement. This is a key building block. Look, to build a quantum computer that can solve truly world-changing problems, it has to be fault-tolerant. And to make it fault-tolerant, you need these high-quality magic states. This experiment demonstrates for the very first time how to actually create them at the logical level. You see, by proving that magic state distillation is an engineering reality, that it's not just some abstract theory on a blackboard, the path to building large-scale, fault-tolerant quantum computers becomes so much clearer. And this isn't just about building better computers. It's about creating the tools we need to design new medicines, to discover incredible new materials, to unlock the mysteries of the universe. So the question is really no longer if we can build these powerful machines, it's what profound problems are we going to solve with them first.